Good morning, everybody. Okay, it's good to see you after the Moon Festival. So, have you had a very good, wonderful rest in the past weekend? It's good. Okay. So now we are going to go to the second topic. The second topic is we are talking about the scaling law. So it's a very important topic. So talking about scaling law, actually, I mentioned last week we don't have a intuition in micro or smaller scale. So in this class, I'd like to introduce some of a basic idea and also what's the difference between the large scale and the small scale. Okay, so before we go to that detail, we can take a look at this table. This table talking about the different scales. Okay, so ranging from very small scale to large scale. So human being is at the center, so we call the meter scale. Okay, so the meter scale is in 10 to power 10 Armstrong. This kind of scale level. Okay, it's in here, at here. Okay, beyond this meter level, we have different scales. Okay, ranging from 10 to 10 Armstrong up to 10 to 36 Armstrong. That means the universe. Okay, so our universe is much larger than the human being, and between them we have many different objects. Okay, so smaller than the universe, we have different galaxies. Okay, and also like a different Earth, different suns, and different objects, huge objects in the universe. And also in the human being range, we are more familiar with the range about like three order of magnitudes larger than the human size. For example, like a bridge, it's like a kilometer range. Okay, and we are familiar with the large one up to like bridge. So beyond bridge, there are many other objects in the universe. However, we need to use some kind of different tools to study them because they are far away. Okay, and too large. And then below human scale. Human scale is in the meter scale. So we are familiar with the smallest ones, like 3 order, maybe 2 order, 3 order magnitude, orders of magnitude smaller than human scale. For example, like a millimeter size of human hair. Human hair is quite small already. And also like ants, like small insects. Okay. So the comfortable range inside human life cycle is from 3 orders magnitude larger than human's scale, and the 3 orders magnitude smaller than the human scale. Okay, so that means human is in the meter range. So we are familiar with the size as large as like a kilometer range, between kilometer and down to like a millimeter. Okay, from millimeter to kilometer. So these are 6 orders magnitudes of scales are the human scales, which all the humans are living inside this kind of scale. However, beyond this scale, you still have a lot of things. Okay, so for example, large things I will talk about universe. So for the universe, you can see it's like more than 30 times of order magnitudes larger than our comfortable zone. Okay. And below this one, not only the millimeter size, we still have a lot of things below millimeter size, like something in the micrometer size and some in the nanometer size. So if we use a human meter size as the orange, the position, the 0 position, we can find out roughly around like 36 order magnitudes. So beyond human's scale, and they are around like 10 orders of magnitudes below human scale. So roughly 1/3 here and 2/3 here, right? Okay. So if you consider this scale, each scale as like 1 unit, we have 32 units here and roughly 10 units here. So 1/3 or maybe 1/4 here and 2/3 here, or 3/4 here. So in this case, we are not familiar with things below millimeter size. So we still have a lot of scales to explore actually. And there are a lot of interesting things hiding inside these scales. Okay, that's why in the past week we talked about Richard Feynman's very famous presentation about there's plenty of room at the bottom. So you can consider below millimeter size, we still have like more than 7 to 8 orders magnitudes. We can have some exploration. So that's why it's important actually for us now to have some understanding what kind of physical phenomena below this kind of range. Okay. Okay. So when we talk about the smaller scale, we like to compare two different types of animals. For example, like a human is one of kind of animal, and the other one ants. So we human are in the meter scale. Okay. The ants usually at a millimeter, even smaller scale. Okay, so some ants are larger than centimeter size, but most of them are millimeter size, and sometimes even smaller. So when we compare the behavior and also the environment they encounter, we can find out very interesting things. For example, when we compare ants to human, first, the ants can easily lift 10 times its own weight. Okay, but for human, how about you? How do you think? How much you can lift? Maybe your own, I think, right? So you barely can lift the other people. Only for some expert, they can lift 2 people at the same time. But most people can lift only another 1 people at one time. Okay, so you can see the difference between ants and the human in the lifting. So ants can lift 10 tons of his own weight, but human can barely its own weight. The second one, so when ants are falling from high, it will not be injured. Okay, so for example, if you can do some experiment, if you to cast out one ant from the first floor, come down to the 0th floor, so you can find the ants no problem, so you can walk away after you just fall down. But for human, if you jump from here, what will happen? There'll be serious problem. Okay, you got a serious leg broken or maybe life threatened. So this problem. So you talk about falling, the ants will not have some problem, but for the human, is easily injured. Okay. Okay. So the third things are some ants can fly. Okay. Especially during the mating season. Okay, you can see the usually the male. The male ants can fly, and to find out the female ants and do the mating. So it can easily fly, but human wish to, but it's very difficult human to fly. Remember how long we have spent to learn how to build up tools to allow us to fly. If we want to fly by our own, it's not possible actually. We don't have that kind of structure, and also our muscle is not strong enough to support this kind of action. So we wish to, but we cannot by ourselves. We need to use some tools. But for ants, they don't need the tools. Okay, they can fly by themselves. Okay. Okay, so when we compare the first three, we feel very upset for human. Compared to ants, we are nothing. Okay, so we even cannot do the everyday ants life. Okay, so that's a problem. However, and also when we compare the ants, the body's size and structure to humans' body structure, we found that ants, even the leg is thin, it's pretty thin. Even it can lift 10 times of its own weight. But compared to his body, his legs only like one-fifth or one-sixth. It's pretty thin. The human has a very thick leg compared to your body. It's like one-half. So we got very upset about these effects, actually. However, we will talk about later on. One thing we will be better than ants. For example, you want to take a bath, take a shower inside a tub, okay? You won't feel problem when you want to get out from the tub, okay? But for ants, if you put ants into the water, okay, a tub full of the water, so ants will get some trouble. They cannot get out easily. So there's a problem coming from surface tension issue. So you think we are two different animals living inside the same world, same universe. How come we encounter different phenomena, different situation? Also, we face the same physical, equations. Actually, when we look into the equation does not give you different equations. We use the same equation to describe all the phenomena. Okay, but in different scale, you have different phenomena. How come? Okay. So from this example, we found out we do not have very good intuition. Okay, intuition, 直觉. Okay, of a micro scale physics. Okay, our intuition is based on our own scale. So remember from the table, our scale is the meter size. So our everyday life give us the examples and also experience in this 6 orders of magnitude scales, as large as a kilometer, smaller as small as like a millimeter. But between millimeter and a kilometer, this is our comfortable zone, and this is the region we build up our own intuition. However, if we talk about the phenomena below this kind of range, below millimeter size, or even larger than kilometer size, we don't have a good intuition because our intuition based on the meter size. Okay, so this is a problem. Okay, and also if we got this kind of problem, we always come back to a real physics, the real equation, because the equation will not lie to you. Okay, so we usually use our known physical concept, classical physics and the continuum mechanics to do some dimensional analysis. The meaning of a dimensional analysis is we use the same equation, but we do some calculation, do some estimation under different kind of scale condition. So the physical phenomena will become different. You will find the result different. I will tell you how. Okay. So we cannot count on the intuition. So we need to come back to the physical concepts, the classical physics, even continuum mechanics, or even quantum mechanics. So if we want to do the scaling analysis, we need to come back carefully to each of the individual physical quantities. For example, like a force, like a mass, and a volume. What's their fundamental meaning? Okay, then we will do some comparison when we try to scale up or scale down. Okay, they will behave differently. Okay, so first we will define, talking about the scaling analysis. So force, mass, volume, and also different kind of physical quantities, they scale differently. Okay, so we can use the length scale, use a very simple symbol to represent the one-dimensional length scale. We call it L to power 1. Okay. Assume the system is an isometric system. I will discuss about what is the isometric and allometric system. Isometric system, that means we blow up the object by similarity, okay, condition. So that means that we blow up the things in 3-dimensional, okay, at the same time, and also in the same scale, okay, in the same quantity. Okay, so for length, the length scale is usually the power is L power to 1. Okay, for the area is the L power to 2, and the volume L power to 3. Okay, so length scale. So we will talk about the power only. It's a line scale. It's only L power 1, 2, and 3 for area and the volume. Okay, so when we talk about different force, okay, surface force. Okay, we have different kind of force: body force, surface force, line force. So when we talk about body force, so the force will be equal to the power 3. Okay, and talking about the surface force, the force will be the length scale power 2, and for the line force, so we will the scale will be power 1. Okay, so when we look into different scales of the different forces, for example, like a mass. Mass is proportional to the volume. The volume times the density, right? We call the mass, and the mass is proportional to the volume. So the volume is a kind of a body force. The body force means it's proportional to the volume. Okay, the length scale to up to 3. Okay, so it's body force. And then the other different force, like the skin friction force. Skin friction force talking about the surface. If you have a larger surface area with more skin friction. Okay, so it's a kind of a surface force. Okay, so it's proportional to the surface area. It's the length scale, the power 2. And about heat transfer. Heat transfer is also count on the surface area. Okay, so we have a larger surface area, we can have a more heat flux. Okay, heat flux is surface area times your the temperature gradient. Okay, and the diffusion is very close, similar to heat transfer. The heat transfer we talk about, there are temperature difference. So we will have heat flux from one higher temperature site to have heat flux to a low temperature site. But for diffusion, we are talking about the mass. We have a different concentration. We have a high concentration area, low concentration area. So the mass will flow from a high concentration area to a low concentration area. So the mass flux, okay, diffusion is kind of mass flux. So it's very similar to the heat flux. So it's proportional to the area times the concentration gradient. Okay, so it's also surface dependent physical phenomena. Then the third one, muscle strength. For the muscle strength, it's not depends on the volume of the muscle. Okay, it depends on the cross section of the muscle. Okay, so you have a large area of your muscle, you have a stronger muscle. This is also a surface force. It's not the body force. Okay, remember. So the bone strength similar to your muscle strength. It's also proportional to the surface area. Okay, the second power. So this is some fundamental physical quantities which give you some. I just give you some very fundamental view of the original scaling phenomena, scaling effect. So later on, I will try to do some analysis based on this kind of basic conditions. Okay, so we can have some understanding here. Now I will go to two interesting concepts. We call the isometric concept and also allometric concept. So isometric concept, the meaning is we blow up things by the same measure in different scale, in different direction. Okay, so we are three-dimensional things. So if we blow up things in three-dimensional manner and also in the same ratio, the system means isometric system. So when you blow up things, things will look very similar to you original things. So it's like a similarity condition. So this system, if we blow up things or shrink things by the same measure in three different directions, we call this an isometric system. So compared to isometric system, allometric system means we blow up things in three different directions with different measure, different ratio. So that means the final things will not look very similar to the original one. You may be lengthened, stretching, or maybe become fatter, okay, because you blow up in different direction with different kind of ratio. So this kind of system we call the allometric system, okay. So if we put into the equation, as a metric system, we can put down like y equal to b times x power a, okay. So if a, the power a equal to 1, that means it's a linear scale, y proportional to x. X means one of your dimension. For example, x represent your height, okay, and the y represent your width, okay. So if we have twice of the height, and we also blow up twice as your width, so end out you will find a similar person with different size. One's taller person, the other one is a shorter person, but they look similar, okay. So if you do this way, the system will call the isometric system, okay. So a equal to 1. However, if a is not equal to 1, that means when you have twice of the height, that means the x dimension, the y dimension, your width, blow up only 1/3 more, 30% more, for example. So you will look thinner, longer, taller, and thinner when you blow up twice of your height. So in that case, the power a is not equal to 1, okay? So you blow up in 3 different dimensions in different measure, different ratio, okay? So this kind of system we call the allometric system. I think, this is a new concept, so I think it's not easy to understand for the first time, okay? When you look into the different species, different animals, different plants, okay, so you find out that actually we have an isometric system inside the same species. For example, like a human, we have a taller human, shorter human, okay, but they look similar, right? The ratio looks similar. But if you compare different species, for example, like an ant compared to human, you find the ant structures very curious, very odd, very interesting. It's very different from human because they look thinner on their leg, right? They have a very huge body and a very thin leg compared to human. Okay, so between two different species, okay, actually the different animals, they were built up by using allometric system. That means they blow up their legs and the width of legs different from human being. Okay, so for isometric system, remember they are similar structure. When you blow up the structure, they look similar. Okay, the allometric system that does not look similar. Okay, maybe thinner or fatter. Okay, depends on your formula. Okay, so if I put it into a formula, remember, okay, the power, the difference is the power, the power a here. Okay, so if you have a equal to 1, y, the other different kind of dimension will be the scale dimension will be proportional to the first one. For example, your length, your width will be proportional to your length. That's called the isometric system. If a does not equal to 1, okay, so the width will not blow up similar to your length. Okay, they will have a different measure. They call it allometric system.